The changes I made is I changed the title from what was published, and then I changed the content to match the title. This is joint work with Amit, Andrew, Justin, and Suresh, some constant fraction of whom should be in the room at the moment. So we start with this piece of boilerplate legal text from a cloud computing service very much like Amazon EC2. It's the kind of thing that you never click on, you never read, you just click past. But if you actually stop and read it, it sort of says, we make no representations that this will be uninterrupted, will be free of harm. You look at this and you think, well, are they promising anything at all? Right, this is a cloud computing service. Will it actually compute whatever I ask it to? Or will it just, take my money and do nothing? All right, so that's sort of all the motivation there will be for this talk, because the question it prompts is to say, well, could there be a guarantee? Could there be a guarantee of correctness for your computation? Right, ruling out sort of the obvious things. So, one way I could check correctness of the cloud computation is I could take my laptop and try and repeat the computation myself and see if I get the same answer. Well, that would kind of miss the whole point. And because we are being sublinear today and tomorrow, I also want to do this without storing a copy of the whole input. I want to say, can I just keep some summary, some sketch of the whole input that would let me check someone's computation over it? So the answer is yes to these questions. Otherwise, this would be a much shorter talk. And so what I'm going to talk about is some results in this area. This is quite a big area generally, and even just the sort of the streaming take on this area has had quite a few papers. So this is some work from the recent Complexity conference. So if you think back to the distant time of the 1990s, you'll remember that there was this trend of excitement around interactive proofs. And actually, if you think about what we want to achieve here, what we want is something that looks very much like an interactive proof, right? We want to sort of pose our question to the cloud, say, well, here's the data, here's the computation, go off and do some calculation for us, and we sort of wait for a while, and the cloud pronounces, right, here is the answer to your calculation. This is the complete, correct, and absolutely right answer. So we then want to actually have some further interaction. We want to say, well, prove it. All right, don't just tell me the answer, prove that this is in fact the answer. And then, the pattern of communication might be, the cloud gives us some claim, some statement, and we might respond to that with some sort of question. We might sort of say, well, what about this bit? And we'll get some response, and after some number of sort of claims and questions, hopefully we'll reach the point where we believe that this is indeed the correct answer, we accept the originally claimed answer, and we can move on. And although this is sort of somewhat cartoonish, this is pretty much the actual outline of the protocols that we develop, right? Only a small constant number of rounds of interaction before we either accept or reject. So this is what the model should look like. We've got two parties, the weak verifier, the powerful prover. They both see the same input, which we'll think of as a data stream, just like any of the other streams we'll look at. So at some point, the verifier wants to know some computation on the stream seen so far. They have some interaction between them, which may be over one round or multiple rounds. And so we get this proof of the claimed answer. And you will sort of enumerate these as we go on, but we then want to think about what's the probability that the powerful prover can fool the verifier. We'll worry about what are the resources that the various participants use. And I'm not going to get too deep into this, but there are some really nice connections to communication complexity, to this sort of various notions that have come out of interactive proofs. But all of this is done with additional streaming constraints. So we want this to be really done by a very weak prover, a verifier rather, against potentially a very powerful prover. Okay, so one of the things you want to do here is think about what are the kind of problems that this would let you solve. And so the first question we think of as sort of streaming people is, well, what's our canonical hard streaming problem? And what can we do about that problem in this model? So I'll talk about two problems today. And the first one, like Piotr, needs no introduction. It's the index problem. So we see a long stream of binary bits, and at the end we see some index that says retrieve a particular point from what you've seen already. Tell me whether it was a 0 or a 1. Okay, so we know this is sort of our canonically hard in one pass streaming problem. Can you come up with a protocol, a scheme that would let you answer this in this variant model? The other problem I'm going to talk about is slightly less toy. It's still very simple to state, very clean. It's a nearest neighbor problem. So a similar setup. Our input starts off being a bunch of points x, where these are residing in some fixed and typically well-behaved metric space. And at the end, we'll have a query. That query is going to be some query point y. And we want to say, well, which of those points x that came already happens to be the nearest neighbor of that query point y. Okay. So I said there are some parameters that we'll care about. Pretty much anything you can parameterize here is something you can put into some kind of big table and enumerate all the possibilities. So we want to make sure, being streaming people will sort of fixate on space as the main characteristic of these things. So we'll look at what's the space the verifier needs to keep some summary of the stream. So obviously we want this to be sublinear in the size of the m input points. The prover space we won't worry about, and in general, because the prover is going to solve problems that are canonically hard in the traditional stream model, we might as well assume that they store the whole input. The verifier and prover will have their conversation to determine the answer. Again, you can play around with the probabilities here, it doesn't matter too much, but in general you want an honest prover will always convince a verifier that they have the right answer, and a dishonest prover will be unlikely to fool the verifier, right? So this 0.99 probability, it could be 2/3, it could be 0.9999999. It doesn't really matter. It doesn't actually cost very much to reduce the probability of making an error. So I say lots of things you could fixate on. We'll mostly look at what's the space cost of the verifier, the cost of the communication in terms of number of rounds of interaction, and actually the amount of information communicated through those rounds. Okay.
So maybe ask that.
Sure.
What are the computational restrictions on the prover and verifier? In terms of time.
Yeah. So I'm not putting computation. So in general, because we're interested in sort of getting this kind of result, we're kind of going to try and construct protocols that are robust against an arbitrarily powerful prover, right? So if you're sort of into the crypto world, this is we're actually looking for information theoretically secure kinds of protocols. Mm-hmm. We're not even making a sort of polynomial boundedness assumption about this guy. Verify, you want him to be pretty efficient, and what I'll show you happens to be like that. And lastly, okay, you could have a computationally unbounded prover, but you'd kind of like it if the prover an honest prover could run these protocols in a feasible amount of time, and that also turns out to be the case. So, yes, this is reasonable, for some definition of reasonable. Okay, so the first thing to do is just to say, well, can we do anything at all in this kind of model? So let's do a very simple upper bound for index. So remember, we have this long binary string. Let's assume for the sake of simplicity that we know how long it's going to be. So what we'll do is just chunk this into different blocks, right? So chunk the input into blocks, keep a hash of each block, right? For flexibility, this can be a linear hash, so I don't actually have to see the data arriving in any particular order. I can just keep all my hashes in parallel and update whichever one I'm seeing updates relevant to. Okay, so that this is what the verifier is doing. The verifier is doing this blocking, keeping hashes. At some point then we say, oh, I want to know which bit this was. I don't remember anything about this block apart from the hash on it, so I'm going to need some help here. So the prover helpfully or unhelpfully tells me some sequence of bits. And the verifier then has to check, well, do I believe that this sequence of bits that's claimed corresponds to this one? Well, I know the hash function, so I compute the hash of the revealed set of bits against the stored set of bits. If they agree, then I'm reasonably convinced that I'm not being lied to, and so I can extract from this set the relevant bit and output it. Okay, so what are the costs here? Again, focusing on sort of the space. Blocks of h bits, so an h bits of proof. The number of hashes is m over h, so you get a nice trade-off, right? And you do the usual thing, you balance these two. And basically you get sort of root n blocks of length, roughly root n bits. But you can play around with that. So sort of root n space. So already that's not too bad. Right? Already that's better than the linear lower bound you'd have for a traditional model. Your polynomial, but you can argue that square root n is sufficiently non-scary polynomial that you might even be happy enough with that. But could you do better? Right? Is this actually really a polynomial problem, or can we get it something smaller? So that was one round for index, right? So one round meaning the only communication really between prover and verifier is when the prover claims these and implicitly the verifier either accepts or rejects.
A really simple question, right?
Mm-hmm.
Well, what stops the prover, the malicious prover, to find something else in the preimage of your hash function?
Yes, so okay, good. So the important thing here is that the prover never has to know the hash function, so I don't reveal the hash function. So that's my randomness. That's the verifier's private randomness. So the other important thing, which you obviously saw and anticipated, is that there's no communication of that private randomness from in any form from verifier to prover. Okay. So could we do any better? Well, if we go to 2 rounds, we can do something different at least. So here is where my PowerPoint skills fail me, because I'm trying to illustrate a b-dimensional hypercube, and I'm sticking to 2 dimensions to show that. So you're going to have to use your imagination a bit here. So what we do is we take that data and we re-index it into the Boolean hypercube. So this sort of rectangle with dots is my best drawing of a b-dimensional Boolean hypercube. Okay, what does that mean? It just means that any index expressed in binary tells me, the first coordinate is a 0 or 1, the second coordinate is a 0 or 1, and so on. So that indexes me into here, and this sort of picture is trying to show, here's my Boolean hypercube with sort of 1s and 0s in it. What we'll do is we'll do this trick, again, that sort of draws on ideas from interactive proofs, that says let's actually think about the extension of this input, right? So here this is indexed over sort of 0, 1 to the b. I can think about the space that's actually indexed over some arbitrary field to the power b. So rather than 0 or 1, it's got arbitrary, let's say, integer coordinates, b of them. And I can meaningfully think about my input data extended out here. Right, so the intuition here is to say, I know if in 1 dimension I tell you a bunch of xy points, I can draw a polynomial that goes through all those and extrapolate that polynomial to any arbitrary location. I can do the same thing here, right? I can think about this sort of multi-dimensional polynomial extension of the input, right? And that, in fact, there may be multiple choices here, but I'll take sort of the canonically simplest of those. So based on this area where the data is defined, I can pick any point here and work out what that is in this polynomial extension. Right? So I'm kind of indicating this here with the colored points, because while this is maybe restricted to binary, these are arbitrary field values defined. Yep.
So you have the stream coming in.
Yes.
You're encoding it as a single point in a Boolean hypercube, a set of points.
Okay, so let's get to the protocol and come back to that question if it's not clear. So I'm saying that in principle it can be extended to here. So this extension is well defined. My protocol then is to pick some point in that space. And I'll have the verifier pick that with private randomness and evaluate this extension at that one point. Okay. And I'm going to have to come back to this because I'm going to have to tell you how to do that. But for now, let's just assume you can do that. So we've picked some secret point. This is going to basically be our check, our way of testing, and evaluate the extension of the input way out at that point. Then we figure out what the query point is. We're told, or we work out that this is the point that we want to know about. Right? So back in the nice, warm, comfortable realm of the data, look up some particular point. So again, you can kind of use low-dimensional geometric intuition and then check, does that translate to higher dimensions? In this case, it does. So between these 2 points, in traditional Euclidean geometry, there's a unique line that links them. Likewise, in this sort of multidimensional field geometry, there's a well-defined unique line that links them. So when I say line, I mean, a constant plus a multiple of an offset, linear multiple. So, the constant might be this query point, and offset stepping you through the points in the field. So the important thing here is you can work out this line. This line doesn't pass through too many points in the original data, and it passes through a lot of different points in the extension. So the verifier works out, again using sort of simple algebra, what is this line, and sends the description of this line to the prover. Then the prover has to work out, well, what is the input restricted to this line? Right? In other words, I can parameterize the line by my usual scalar alpha, and then as a function of alpha, what's a polynomial that for alpha equals 0 tells me the value of the input at this point, for alpha equals 1 tells me my value here, and so on as I step through. And the important thing here is that this line restricted to, the input restricted to the line as I take it through the extension is equivalent to just taking the points in the input that the line hits and looking at the extension of those, right? Things sort of commute in just the right way that you'd like. Okay, so I now have a line that goes through a whole bunch of other points outside my input, including this one that that the verifier selected as the location to check. So the verifier can then do that check that this line that hits lots of different points, where it hits this point, evaluate this claimed polynomial, see does it agree with what the verifier evaluated for themselves. If it does, then it's quite likely that the prover isn't lying. And it gets back to, like Amit was saying, a sort of a short Zippel kind of argument that says if it's not the polynomial you thought it was, because it's low degree, because of the thing I was saying about it not hitting too many input points, then the chance that the difference between the wrong polynomial and the right polynomial happens to be 0 at the random place where you checked it, is just a function of the degree of the polynomial, which is small, divided by the size of the field, which is easy to make as large as you want. Okay. So, basically I've got my check here. If my check agrees, then I use the same polynomial to give the answer that I want. Right? So, a couple of rounds of interaction between prover and verifier to get this protocol. Okay. So for all this to work, the critical bit really actually is here, that the verifier can do this evaluation of the low degree extension of the input of randomly chosen location. And the reason that I kind of really like this result, and I think it's something that should actually be of broader interest to this community, is that this is a completely streaming operation, right? It's a complete linear transformation of the input in a very sketch-like way, right? So I'm trying to say, what's my evaluation of the extension of the input? Well, initially, the input is 0, and my extension is 0 everywhere, right? So my initial evaluation is 0. That's easy. Then it turns out every update I can treat independently, right? So I just have to add on the cumulative effect of all the updates, right? So that's sort of my linearity kicking in and helping me here. So if I just think of a single update that says something has happened at a particular coordinate location, so this update y has these sort of B binary coordinates. So that's an impulse, a 1 in one location. I can think of it as just sort of being that impulse that's sort of a 1 at that location and 0 everywhere else within the Boolean hypercube. Right. Well, then I have to think about what's the polynomial that looks like that, the polynomial that's 1 at one location and 0 everywhere else within the Boolean hypercube. That's actually quite easy because it's just that polynomial that sort of is 1 minus the coordinates where my element is defined, so that I get a 0 contribution if I evaluate this at any place where any of the coordinates differ, right? With the scaling factors, but basically this. And then the evaluation of that polynomial out at my location, my random location, basically sort of drops into this polynomial here. So this even has a nice name, right? This is a Lagrange polynomial, and I'm just updating linearly my evaluation of this incrementally as I step through each of the updates by doing this sort of simple coordinate-wise multiplication. So that B is small. Remember, B is sort of logarithmic, number of dimensions. So it's really nice. And so this is nice, linear, fast to compute, easy to evaluate sketch of the data that gives me this ability to check certain kinds of computation. And actually, although we use this in this one particular case, this sort of evaluation of the extension of the input comes up over and over again in these kind of interactive proofs. Okay. So I kind of covered this already. If the prover is honest, V will always accept. If the prover is dishonest, easy argument says that small probability of being fooled, and easy to control that probability. And actually very nice then, because you go through all these things, everything was low dimensional, everything was low degree. So you're talking sort of essentially polylog cost for all of the costs you can enumerate. Yes?
Do you actually store the polynomial? Does the verifier actually store the polynomial?
No, this is the whole point. The verifier doesn't store the polynomial at all. They're only ever storing an evaluation of the polynomial. And what I'm saying here is that you can incrementally, so Q is your evaluation of the polynomial at this random location, and you can incrementally update that as the input changes. Okay. So you get this nice thing, you get this exponential improvement over one round, going to 2 rounds. So being sort of streaming people, you can immediately say, well, once I can do index, there's various kind of encodings that let me do things like median and other quantiles by sort of reductions. What about more complex things? Okay, so I think I really need to speed up and finish off. So I said nearest neighbor. You've got your points in some, let's say, nicely behaved space. So let's say n integral possible coordinate values, d-dimensional space. Let's also assume that your well-behaved metric keeps your distances to some polynomial set of possible values. So what you can do is say, well, actually, nearest neighbor can be proved to you by a couple of lookups, right? So we do this sort of rewriting trick. If you think about all possible balls, right? A ball is defined by a center location and a radius. We'll do this thing that looks kind of crazy, but fix it on the next slide. Convert the input points to a virtual set of balls from the set of all possible balls. So take each input point in this nearest neighbor instance, replace it by every single ball that it's a member of. Okay. So that's an enormous blow up of the input straight away. But okay, you can do that. if you choose to. Then just take that sequence of balls, process it through the existing index protocol. So you're now doing an index where the index itself is a ball. You're looking up, did I see this ball or did I not see this ball in this virtual input? A nearest neighbor query with a prover then becomes a couple of lookups, right? So you look up, someone says, the prover says to you, this is my claimed nearest neighbor for your query. So you say, well, firstly, does that point exist in the inputs? That's one lookup. And secondly, if I look at the ball centered on my query with the radius just less than the radius between the claimed nearest neighbor, that has to be empty, right? That I didn't see anything closer. Okay. So that works, that's the correct protocol, but you have a huge blow up, right? So that's really going to cost the verifier in terms of time. So it gets back to the original question about time. Because if I actually have to literally enumerate every single ball that each input point is a member of, huge, huge blow up. So the insight here is that I can do that translation cheaply and by sort of virtualizing it. So let me sort of try and say at the highest possible level what goes on here. It relies on the fact that we're going to deal with well-behaved fixed metric spaces. So assume that the metric space is something simple like Hamming space or Euclidean space or something like that. So if that's the case, then the function that takes as a parameter a particular ball, which in turn is a radius and a center, and a point, and tells you whether or not another point falls inside that ball, has a nice simple description, right? It's a simple mathematical function, it's a simple circuit. And what we want to do is we want to query the vector that's indexed by balls where we sum over all the data points of the input, whether or not any of the input points fall within that ball beta. Right? So we do this, again, another trick borrowed from the interactive proof world that says, well, let's go from this function represented as a circuit into a polynomial by doing sort of the obvious things. Intersections become products, disjunctions become the right kind of rewritten product as well. And we work entirely in the low degree extension of this extended vector indexed by balls. Right, so you're looking at this sort of low degree extension of this polynomialized thing indexed by balls which have the right number of coordinates, which is again a summation over this circuit transformation of the input and the balls. Okay, a little bit fiddly, but the main thing is you can sort of work entirely in this virtual space. You can apply the index protocol to this process, and the crux of it all is that you never actually have to materialize this huge blow-up of the input. Right? So if you think about it, what's happening, for example, at the verifier side, the verifier is doing their evaluation of the extension, but their extension is sort of extending the indexing of the balls, so they're just extending, again, sort of one particular coordinate far away that happens to be in this re-indexed system, and they can take all of each update and sort of run it through the polynomial that they get to the right place. Okay, so with a bit more hand waving than I particularly wanted, the claim is, the verifier, I can still do this efficiently polynomial in the dimensionality of the space and log of the size of the coordinates, and the communication cost and verifier space are similar. So after all of that hand waving, I claim that these things are actually still really quite practical. Implementable, although I don't think implemented. Lots of deep connections to communication and interactive proofs. And still lots more things to think about here. We kind of came at this thinking about what are some interesting sort of real world-ish problems, so that's why things like nearest neighbor are nice things to look at. We don't have much ability to give useful lower bounds within a particular class. So if I say, what's a lower bound for a 2-round interactive protocol, we don't really have many tools to say much about those. And you can also look at lots of variant models. As soon as you bring in things like multiple provers, then you need a whole new set of techniques. All right, I think I had better stop there. Thank you. General recipe. There's a couple of approaches. So we've looked at sort of problem by problem. There are more general techniques that work based on sort of taking arbitrary circuit constructions for a particular problem. Those then bring in lots more rounds because essentially you look at layered circuits and you do sort of multiple rounds of interaction to take you up through each layer of a circuit. So you can actually do some more general purpose computations, but you lose quite a lot in terms of the costs. So there's sort of work in both directions.
All right, thanks, Graham.
Thank you.